takes a lot to change the temperature of water. So it keeps land masses nearby relatively temperate. They don't have huge swings in temperature. Even Anchorage, Alaska is not too bad a place to live if you're going to live in Alaska. Okay. Now, if you move, anybody been to Fairbanks, Alaska? Tell me about Fairbanks, Alaska, and how much water's near there. Like nothing, and tell me about the temperature swings. Yeah, it goes from high to really, really low because Earth, or dirt, doesn't have a very high heat capacity, so it changes temperature readily. Okay.
What's the capacity? I mean, keeping the heat?
Yeah, it's how quickly, really, we can change the temperature of an object with a given energy input. Actually, this is kind of stated backwards. I'll show you some graphs and we'll talk about it in a second. But realize that different things have different heat capacities. Okay. We'll mess around with some solvers here in a second. I do want to talk about calorimetry a little bit. How many of you have ever done a calorimetry experiment? You haven't? You haven't taken chemistry?
I have, but it's
You're
been
not
a
going to
while.
raise your hand.
I don't remember.
Calorimetry? All right, so here's the idea of calorimetry. We have an isolated system. This means no energy can leave the system, okay, or enter the system. Whatever energy it starts with is the energy it ends up with. So typically what you'll do is you'll take an unknown object, let's say, and you have some known mass of water, and you might, I don't know, have, what did they say? Yeah, so the hotter object will have an energy flow away from it toward the lower temperature object. Does that make sense? And they're going to exchange energy in this whole process. Okay. And by messing around with calorimetry problems, we're able to determine the specific heat capacity of different materials. So what I'd like to do is talk through one of these examples and show you how this is done. Okay. So this is one I'll actually work through because it's actually useful. Okay, so it says we have a calorimeter made of aluminum. So mass of aluminum equals what? 1.5 kilograms, right?
Mm-hmm.
Okay. And it has mass of water is what? 0.2 kilograms. And the water and the cup have the same temperature. So T initial of H2O equals, and that is the container, aluminum cup. Oh, equals cup. Do they give us the original temp? They do. 18 degrees Celsius. So what am I doing? I'm just writing out known information. M of unknown is what? 0.04. Those guys are having a test today. They're all nervous.
Mm-hmm. They
The
were
material
so-
is heated to temperature. Bless you.
Oh, I just pinned it.
Anything else I need to know? After thermal equilibrium is reached, the temperature of the water in the cup and the material is 22. So T final of all of it is 22 degrees Celsius. We want to find the specific heat capacity of the material. So this is typically what you'll do. You'll take an unknown material, you'll find its mass, you'll add it to a known quantity of water, and you have some aluminum container, and we're assuming it's isolated from its surroundings, so no energy leaks out and no energy is taken in other than exchanges between the three objects in the system. Does that make sense? All right, so just using your spidey sense, right, which direction is the energy going to flow?
Out from the unknown material into the water,
And possibly into the,
into the can as well.
correct. Does that seem reasonable to everyone? Okay. And I will tell you that in an isolated system, the heat lost plus the heat gained by the different pieces has to equal what? If some things are losing heat and some things are gaining heat, the sum of those values must equal zero, because we have an isolated system. Okay, energy can't disappear or appear in our system. The sum of these exchanges has to equal zero. So this is how I would recommend you set up your problems. Some people will say heat lost equals heat gained. You can do that, but you have to be careful with this, with your subtractions. And I'll point that out as we go. Okay. So we kind of know, our spidey sense tells us that this is going to give off energy because it's at a higher temperature, right? So remember that Q is equal to MC delta T. So this is the object that will lose the heat. Oh, question?
Never mind.
Oh, okay. This is the object that will lose energy. So how would we express that equation for the object that loses energy? We would say mass of the unknown, or what is it, 0.4, times specific heat capacity, I'll just call it C. We actually don't know what it is. That's what we're trying to find, correct?
Correct.
Okay? And what is its final temperature? 22 degrees. And where did it start?
80? No.
97, right? 97. So the reason I like to do the problems like this is that it's always T final minus T initial. Always. You can see that value will be negative, which implies my energy is going from the metal to the other pieces. Okay? Now I say plus the heat gained by the various pieces of my system. Okay? The first piece, let's go with the water. How much water do I have? 0.2. What's the specific heat of water? Somebody needs, is it?
4,186.
Thank you. 4186, that's this guy. You following? And now, where does the water end up? 22. So T final minus T initial. You can see just by this calculation that the water will gain energy because this is positive. Does that make sense? And there's one other piece in here. There's an aluminum cup, or the calorimeter itself. How much mass is there?
0.50.
0.15. Can someone look up the specific heat capacity of aluminum for me?
9.00
9.00.
times 10 to the second.
So 900.
No, 9. Oh, yeah.
That's okay. And then where does it start? I mean, what's its final temp?
20.
also 22, and it started at 18. So what happens is we put the water and the aluminum cup together, we let them sit there and equibrate with each other at room temperature, roughly 18 degrees Celsius or so. Then we add the unknown object. What you don't want to do is have your cup and your water at different temperatures. It just makes it harder, but it's not the end of the world. Temperature difference is also 22 minus 18. All of that equals 0. You'll notice in every single case, if I do this sort of setup, it's always T final minus T initial. T final minus T initial. T final minus T initial. If you want to stray away from my advice and approach the problem like this, you're welcome to do so. However, I will warn you that you better get your signs right on the correct side of the equation. Okay, are you following what I'm saying? Yeah. This has got, one of these has got to be negative and the rest of them positive to make 0. Over here, you've got some positive thing equals some positive thing, or some negative thing equals some negative thing. You better get it right. So I recommend doing it this way. Now, notice I have one equation and one unknown. Can I solve for C? Yes, we can do this. So we'll take a look at the number. I think I got this right. So we've got, how did they do it? They did it the way I don't recommend. But the point is, you should get 1300 from my equation if you do the math properly. Okay. So what is the unknown substance? Anyone have a chart? What do we think it is if it's 13 joules per kilogram degree Celsius? Is there anything in there close? Not really.
Not really, no.
Can somebody Google a specific heat capacity of 1300?
Specific heat of 1230, but
1230, okay.
that is sodium, and it will react violently with water, so I don't think that's.
So sodium is one idea.
I got some other ones. I got a whole chart. Cellulose, cotton, wood pulp, and no, that's it. And then let me see. There's another one.
What's the-
Artificial wool, 1350.